Alright, hi all. Very good evening and welcome back to the sixth week of TE live sessions for Artificial Intelligence KRR, Knowledge Representation and Reasoning. Can someone confirm, is my voice clear and is my screen visible? Okay, thanks Ariman, thanks Marak. So so this week we're going to discuss some questions from week 6 content, which will be dealing mostly with an introduction to prologue. Um, So yeah, without any further ado, we can get started. Okay, so the first question that we are going to deal with is based on horn clauses, and we have to select which of the following 5 statements are true with respect to horn clauses. Okay, so this is kind of a recall based question directly from the slides. So yeah, I'll wait for maybe a minute or so, and in the meantime you can feel free to share which option or options do you think would be correct in this case. Okay, any guesses? This is a question straight from the slides. Maybe this will give some hint. Okay, so let's go over the basic definition of a horn clause. So a horn clause is a clause with at most one positive literal. Okay, so there are two parts to this definition: one that it's a clause, and the other that it must have at most one positive literal. Okay, what we mean by that is uh, can be elaborated with the help of these two examples. So here you see that you have negation of P or negation of Q or negation of R or negation of S and then T, which is a positive literal, right? So this is an example of a horn clause, and this can also be rewritten in terms of implication. Okay, if you just rearrange the terms in a certain way, or literals in a certain way, right? So now going back to the options over here, um, let's consider these options one by one, right? So the first one says that horn clause has to be a conjunction of literals with at most one positive literal and zero or more negative literals. Is this correct? Let's say it's not correct, right? Because like we saw, it has to be a clause and it has to have at most one positive literal. So while the fact about positive literals is correct in this statement, but it also says that it's a conjunction, right? And we don't want a conjunction, we want a disjunction, by which we basically mean that we want an or of certain literals or negation of literals, not an and of certain literals, right? So the first two options are, we can say, incorrect just by looking that they mention conjunction. Uh, so what about the other three options? The option C says that it's a disjunction of literals with at most one positive literal and zero or more negative literals. This seems fair. Uh, the option D says that horn clause satisfy the definition of a clause in a CNF formula. This also makes sense because if you remember, one of the conditions for horn clauses was that horn clause has to be a clause, right? It's in the name itself. So obviously a horn clause will satisfy the definition of a clause. And the last option is also correct, which says that horn clauses, when written as a uh, logical implication, have a head and a body, where the head has at most one positive literal and the body is a conjunction of zero or more positive literals. Right. So the correct options in this case are C, D, and E. I hope there are no doubts in this question. It was a pretty straightforward one. Shall we move on to the next one then? So Balaji, can you elaborate on what do you mean by null case? Or null clause?
Excuse me,
Yeah.
sir. It should have at most one positive literals. That is fine.
Mm-hmm.
Then they are mentioning about negative horn clauses. So if all the statements are negative, would it be considered as horn clause because it is coming under negative horn clause, right? In
Right.
case if
So, as per the definition, we have at most one positive literal, right? So that at most means that one or less, which can even be zero, right? So in that case, yeah, it satisfies the definition of having no positive literal at all. So, is that what you were asking?
so if all the statements, for example, all the literals
Mm-hmm.
that satisfies the disjunction criteria, it is given. So
Okay.
it will be considered under negative horn clause. So that is obviously coming under horn clauses, right?
I mean, it is as per the definition, right? Like I said, the definition has at most one positive literal, and by definition, at most means that one or less than one.
Oh, at most one or less than. Okay,
Yeah,
okay, sir. Okay, I got it.
yeah. Like at least means a certain threshold or higher than that. At most means a certain threshold or lower than that.
Ah, okay.
Okay, so you mean a null clause? By null clause, you mean that a clause with zero literals. Okay. Uh, so for that, I would refer you back to the definition of clauses. Would you call a null clause a clause in the first place? Okay, yeah. So, which is the head and body of the implication? So here, see, the option says that when written as a logical implication, they have a head and a body, where the head has at most one positive literal, and the body is a conjunction of zero or more positive literals, right? So conjunction means that it's an and, right? And if we refer back to the examples shown over here, in this case, this would be the body and this would be the tail. Okay. All right then. Um, So maybe this was straightforward. Let's move on to the second question for today then. So this also deals with horn clauses, but a slightly different way of treating them. So here we have to select which of the following options can be expressed as a set of horn clauses. Okay, essentially we have to simplify these options and see whether we can arrive at a representation that is more fitting for the definition of horn clauses. Okay, and one hint that is given is use the rules of substitution to convert to clause form. Okay, so this may require you to work it out by hand. So if you have a pen and paper around, I highly encourage you try to do that right now. And I'll give you a couple of minutes and then we can have a look at the solutions. Okay, so we have a couple of answers in the chat box, and let's have a look at the solution and see which of them we can say are correct. Okay, so for this I'll shift to my Jamboard, and so what we are doing over here is, let's look at the options one by one. Okay, so the first option says for all x, teen x, and there exists y such that owns x comma y and apple y, this whole thing implies happy x. Okay, so it looks complicated, but let's break it down step by step. So the first thing that we're going to do is we're going to tackle this implication over here, right? And we know that implication can be written as so P implies Q can be written as not of P or Q. So that is exactly what we are doing over here. So when we remove this implication, we will have an or inserted, and a not will be inserted before this whole thing, right? Because this whole thing is P in our case, right? So we'll have a not before this, and or happy x. Okay, the next thing we're going to do is we're going to push this negation inside the bracket. Okay, so we'll have not teen x, this or will be sorry, this and will be converted to an or, and we'll have not there exists y, and this whole thing in a bracket, right? Then we are going to further push this negation into the bracket. Okay, this negation of there exists will turn this into a for all quantifier or universal quantifier, and then when this negation goes further inside this bracket, it will make it not of owns xy, this and will be converted to an or, not of apple y, right? So now if you push this universal quantifier to the very left and you remove all the unnecessary brackets or parentheses, you will have something like this: for all x for all y, not of teen x, or not of owns x comma y, or not of apple comma or not of apple y, or happy x. Okay, so this is in the horn clause form, right? We have some negative literals, this one, this one, this one, and we have one positive literal, right, which is this one. So this satisfies the definition of a horn clause, right? So we can say option A is correct. Yeah, there was a hand raise.
Sir, in this option A,
Yeah.
once you convert
Mm-hmm.
to the P implies Q to negative P or Q,
Yeah.
already we see one positive happy X. That won't be that easily changed by any of the parameters.
Mm-hmm.
There itself, shall we stop and then say it is a Harman clause or not?
No, we shouldn't do that, because what if you expand the left hand side and you arrive at another positive literal, right? In that case, it won't satisfy the definition of a horn clause.
No, if there are two positive literals, then it is not a Harman clause.
Yeah, exactly. So as per definition, we need to have at most one, not more than one.
I really, really thank
Yeah.
you, because so far half of the class is over. A Harman class, I was thinking that more than one positive literal.
Yeah.
This at most one means only one. Okay, thank you.
Yeah.
Thank you for the clarification.
Yeah, not only one, it's at most one. So the maximum number of horn clauses, positive literals that you can have would be one. Okay, and yeah, that's about it. Okay, so if option A is clear, then we can look at option B next, which will proceed in a similar way. So here we have for all x, teen x, and so on and so forth. Here also we have an implication over here. So we'll start by simplifying the implication, and we have an or over here and a negation in front, and we go on with simplifying. You can look at the steps and convince yourself that it's proceeding in a sound fashion, and what you'll see is that you arrive at this kind of a last configuration. And again, here you'll see that you have some negative literals, like this one, this one, this one, this one, and one positive literal which is happy x, and they are all connected by ors, right? So again, this is also satisfying the condition of a horn clause. So B is also correct. Now let's look at options C and D. Okay. Again, we'll proceed in a similar fashion. We'll simplify the implication. We'll push the negation inside. We'll convert the existential quantifiers with a negation in front of them to universal quantifiers. Proceed in a similar fashion, and we arrive at uh, this kind of a last statement, which has this structure. Okay, so you can think of it as a and of two parts. This is one of the parts, and this is another part, the first part. Okay, so can you tell me whether these parts, the part 1 and part 2, individually are satisfying the criteria for horn clauses? They are, right, and that's why we'll say that this option C is also correct. Okay, because these two are individually horn clauses as well, connected by this and operator. Okay, so don't get it confused by the earlier fact that we mentioned, where we said that there shouldn't be conjunction. That is a different case. This is a different case. Okay, and as for the last option, here again we proceed in a similar fashion, and we see that in the last uh, representation. So this is where one of the examples that your colleague was just discussing comes up. So here you have two positive literals. Sorry about that. So here you have happy X and busy X, right? So there are two positive literals, and this is exactly why this is not a horn clause. Okay, so the correct options in our case would be A, B, and C. Ariman, I'm sorry, your voice was a bit unclear. Can you please come again? Or maybe you can write in the chat. Yeah, now it's much better. Yeah. So when we're talking about horn clauses, we look at positive and negative literals, right? So we can have at most one positive literal and zero or more negative literals. Yeah. Yeah, that's right. Okay.
Excuse me,
Yeah.
sir. Can you once again say we have a and symbol in that? How it is considered under horn clause? Because we will consider everything or symbol inside the literals. Once again, can you tell me?
Sure. Let's go over that option once more. Alright, yeah. So let's go step by step. Um, so first we simplified this implication or implies, and we had this negation. We pushed it inside. So we proceeded in a similar fashion. We have not of teen. I hope things are clear up until this point, the penultimate step, right?
I couldn't see the screen.
Oh, sorry about that. Is it better now? So what I was saying is that I hope things are clearer up until this second last step.
Yes, yes, fine.
Okay, so here you see that we have for all x for all y, and then we have a bunch of statements, or a bunch of literals, right? Now when we are introducing this for all u for all v, this is just for our convenience, right? Essentially this is just for all x for all y itself. We are just introducing these things for us to separate this into two separate parts. right? Uh, so because we are able to do that, we are able to separate it into two separate parts, and each of these parts individually satisfies the condition of being a horn clause. If we go back to the question, this says that which of the following can be expressed as a set of horn clauses. Okay, remember the question asks which of the following can be expressed as a set of horn clauses. Okay, so this is where you need to emphasize for this particular option. And hence when you divide it into two parts and you get two separate horn clauses, you say that this option C, together also satisfies that condition that is asked in the question, which is it can be expressed as a set of horn clauses. Does that clarify some things?
Yes, yes, sir. So what you mean is it is a conjunction of two horn clauses.
Yeah.
Yeah. Thank you so much. I understood.
Okay, that's great. So to answer your questions, Marak, so if your question doesn't ask you to go with columnization, then it's better to avoid it. So basically what I say is that if you want to do it for your understanding, you can use any method that you prefer, but for answering questions in the assignment or exam, just stick with what the question says, because sometimes there are these very small technicalities in the way the question is framed, and maybe if you attempt the solution via a different approach than what is expected, that technicality might be missed. So just for your own sake, it's better to stick with the way that is asked in the question itself. Okay, so I hope question 2 is also clear. Let's move on to question 3 then. So now we are moving into the territory of prologue. Okay, so just for my understanding, so how many of you have used prologue before, or have some level of familiarity with it? Okay, it seems that prologue is new to everyone, and that's okay, that's great. It's a fun language to explore, so I wish you the best with that. Also, if you haven't already, I highly encourage that you download and install the prologue software in your systems, whichever system you might be using, be it Windows, um, Ubuntu, Linux, Mac, whatever that you are using. There is a version available for all of these systems. I highly encourage you install it and you explore it. And when I say explore, I mean that we're going to see a couple of examples in this and in this live session, right? So I want you to actually try to implement that yourself and see how exactly the steps are proceeding. Okay, and there's also something called trace in prologue, so you can use that trace to see exactly what is going on behind the scenes at each and every step that your program is following. Okay, so okay, I'm going off the topic, but just a suggestion that you should definitely do that, and that will give you a good understanding for the prologue section of this course. Okay, so coming back to the question, this question asks us each option below has a pair of predicates expressed in SWI prologue. Okay, and we have to identify which pairs are unifiable. Use SWI prologue to investigate the term unification. Okay, so again, I'll let you think about these four options for a while, maybe a couple of minutes, and yeah, feel free to share what you think of would be the correct answers, and after that we can have a discussion. Alright, so we have a couple of answers in the chat box, and some of you have got guessed it correctly. And let's have a look at the options uh, of why these which of these are correct. And yeah, online prologue is fine as well. So yeah, let's look at the first option. So the first option says that the two things that are given to us are P Sun and P star Earth. Okay, and so each of these have this constant terms within itself, right? So Sun is one thing that is constant, then star Earth is again a constant, and we know that we can't unify these because for us to unify constants, they need to be exactly the same, right? So option A is rendered incorrect. Option B, on the other hand, has a variable, right, x, and we can assign x to be star Earth, right? So for that reason, option B is correct, and it is this pair is unifiable. As per option C and D, so if you actually implement it in Prolog, or if you actually test it in Prolog, you will see that it will spit out a substitution for option D, but not for option C. Okay, and can anyone tell me why that is so? I can show you the outputs that you are likely to expect in Prolog, and that will be something like this. Okay, so on the top left is an actual screenshot from the Prolog interface, and on the bottom right is the same thing, but yeah, written manually. um, so you see that when we try to check with the third option, it spits out a false, whereas for the last option it spits out a specific set of substitutions. So why is this why is this the case? Guesses are fine too. Okay, so I'll give a hint. So based on these two things that are given to us, the pair that is given to us, try correlating each specific entity in each of these terms to the left and right of the pair to each other. For example, look at this x plus y and 1 plus 2 into 3. Then look at f of z and y, and then look at z and y into 4. So if we have to write it down, we say that x plus y is similar to, or can be substituted by, 1 plus 2 into 3, which would essentially mean that x is being substituted by 1 and y is being substituted by 2 plus 3, 2 into 3, right? Okay, so far so good. Now we have f of z equals to y, right? Based on this f of z is being substituted by this y, and similarly we have the last z over here that is being substituted by this y into 4. Now do you see the problem that we are going to face? So this is kind of a cyclical definition, right? So you are using z, using y to define z, but then you are again using z to define y, right? So which came first, and which do you use to define which, right? So it's a cyclical relation between these two, and for that reason you won't be able to find a proper substitution, and that's why option C is incorrect, and that's why Prolog spits out false in this case. I hope that was clear. Yeah, exactly. Y is a function of z and z becomes a function of y. Sure, Aryaman. So like Smarak put it in a good way in the chat. So here what we have is that y is a function of z, and z is in turn also a function of y, right? So all these, both these terms are intertwined with each other. Okay, we don't know what exactly we substitute them with, right? And to, in order to properly say that a certain z is being substituted with this thing, okay, we need to know y, and again, to know what y is, we need to know what z is. And so so you see this cyclical dependency between these two, right? And because of that, we won't be able to find a proper substitution for this particular case, as opposed to the fourth option over here, which says which for which we can easily find a substitution, right? So here we have x equals to 1, y equals to 2 into 3, we have function of y equals to z, uh, f of y equals to z, okay, where y is 2 into 3, so z is equals to f of 2 into 3. And then you have z equals to u into v, so you can say that u is 2 and v is 3. So you have a proper one-to-one correspondence between all these things to the left and right, okay, whereas in this third option, option c, you couldn't have anything like that. It's for that reason that options b and d are correct. I hope that helps. If so, maybe we can move to the next question then. Okay, great. So here also we have something related to prologue, but a different setting. Okay, so I'll read out the question to you. So here we have a prologue program given to us that defines natural numbers using 0 and a successor function. Okay, so successor function is basically s of x means x plus 1, okay, essentially. And we have defined the less than predicate in three different ways, okay. So the first way is less than 1, this part is one definition. Then less than 2 is another definition of the less than predicate, and then less than 3 is another definition of the less than predicate, okay. And you can treat this colon followed by a dash symbol in prologue to be equivalent to if, okay. So here when you have nat of successor of x, if nat of x, and what this essentially means is that successor of x is a natural number if x is a natural number. And if you want to further simplify this, if x is a natural number, x plus 1 is also a natural number, okay. So this is how you can interpret the definitions in prologue. And what we have to do is we have to select which of these definitions of less than that we have among these three definitions is the correct definition, okay. So what I'll do is I'll give you a hint, okay. I'll give you two test cases to try out for these three definitions, okay. The first thing that I'll ask you to try is check whether 1 less than 2, this condition or fact is being detected by the three definitions of less than. And the second test case would be 2 less than 1, okay. So 1 less than 2 and 2 less than 1. Check these both, try to understand how exactly these three definitions are working, and after that we can have a look at the solutions and discuss the solutions as well. Okay, so we have one answer in the chat box. Anyone else? I'll give you a hint, only one of these is correct. I mean, one of these options is correct. Okay, so let's have a discussion. Let's shift to the Jamboard. Alright, so this is the three definitions that these are the three definitions that we have, and let's test each of these one by one. Okay, so let's first test 1 less than 2. Okay, so as per the definition, let's test less than 3 first. Okay, so the first statement essentially tells us that 0 is less than any natural number, which makes sense, right? So that is fine. Then it says that successor of x is less than successor of y if x is less than y. Okay, so if we substitute this in this value 1 and 2, so if x is 1 and y is 2, 1 is less than 2, and if 1 is less than 2 is true, then we will have 2 less than 3, because 2 is the successor of 1 and 3 is the successor of 2. Okay, makes sense up until this point. Let's check 2 less than 1. Okay, so if you substitute x to be 2 and y to be 1, then the successor of x would be 3 and successor of y would be, which is 1, would be 2. Okay, so 2 less than 1 is not true because 2 is greater than 1, and hence 3 less than 2 is also not true, right? So it also checks that 2 is less than 1 is not correct. Now what about the other two definitions? So when we go for the second definition, this one, here again let's have x as 1 and y as 2. Here we have if 1 is less than 2, then 1 is also less than is a successor of y, which is 3. Makes sense till up until this point. Let's check the other case. So here we have 2 as x and y as 1. So if 2 is less than 1, then as per this definition 2 should be also less than successor of 1, which is 2. But this doesn't make sense, right? 2 less than 2 doesn't make any sense. So here we have encountered a problem in this definition. Okay, so we have noticed one discrepancy in the second definition of less than. Now let's look at the first definition of less than. Here we have successor of x, this whole thing to be 1 and y to be 2. Okay, so if 1 is less than 2, which means successor of 1 is less than 2, then x would be 0 is less than 2. Okay, fine, this makes sense. Let's check the second case. Here we have successor of x as 2 and y as 1. So successor of x is 2 means that x would be 1, and by this definition again we will have reached a condition where 1 should be less than 1, which also doesn't make any sense, right? So we also noticed a discrepancy in the first definition of less than. So the only less than definition that we didn't see any discrepancy was the third definition, and hence we can say that the third definition is the correct definition of less than, which is also what is given here in the answer. Okay, any doubts? If not, then that is great. uh, then we can move on to the next question, the fifth question, which is also kind of similar but a slightly bit more involved.
Sir, I have a doubt.
Yeah, please go ahead.
Sir, how do we interpret that symbol in between those functions?
Which symbol?
Sir, that here in this slide also there is that symbol. That
Those, the colon followed by a dash.
colon and dash.
Yeah, that's exactly what I was mentioning earlier. You can treat that as an if. Okay, so you have an x colon dash y. That means that you can read it as x if y. Okay, let me write it for you. So if you have something like, then you read it as x if y, as in if y is true, then x should be true. Okay.
Okay, sir.
Yeah. uh, yeah, so let's look into the fifth question now. um, so here we are said that we are told that we have to consider the following program with four predicates p, q, r, and s. Okay. And we have to understand what each of these predicates or each of these predicates is doing, the way it is written. Okay. And then we have to choose among these the one that defines the length of a list as a number n. So essentially, if you think of it in terms of a programming problem, you have to write a program that, given a list, that tells you what is the number of elements in that list. Okay. That you have to write in terms of prolog. Okay. So, and you have to choose from among these four predicates p, q, r, and s that are given to you. So again, I'll let you think about these for a while, and I'll give you a hint. Give special attention to how the value n is getting updated in each of these predicates, right? So some of them have an equality, some of them have the word is. So think about that, and then you can say which of these answers you think would be the correct or incorrect ones. Okay, so again, I'll give you a couple of minutes and then we can discuss the solutions. Okay, so let's have a discussion now. So okay, so first I'd like to hear your thoughts. What do you think each of these predicates do? Essentially, what is their purpose? What do they tell us when we apply them to a certain list? Let's say the list is a list of four numbers, 1, 2, 3, 4, okay, or 100, 200, 300, 400. That is the content of the list. So, what will each of these predicates give us as output? What do you think? Let's start with predicate P. Anyone? Okay, so is the definition of predicate P clear, or is there any confusion about that? Like I said, we can look at it step by step, right? So the first thing that is written over here is that P of an empty list is 0, right? Right. Yeah. So let's look at the definition first. Uh, so the first statement of the predicate P says that P of an empty list is 0. So what could this mean? Remember, the question is framed in such a way that you are asked to write a predicate or choose a predicate that gives you the length of a list, right? So it makes sense to, yeah, exactly. So thanks, Mara. So the first statement suggests that length of an empty list is 0, right? That's perfect. Now what about the second statement? So here it says that P of H given head given tail. Okay, so maybe some of you might not be familiar with this notation, so let me just elaborate on that for you. So in Prolog, when you say something like this is just a way of writing a list where H denotes the first element of the list and T denotes the all other elements of the list, right? So if our list would have been something like 1, 2, 3, 4, then you could say that your H corresponds to 1 and your tails corresponds to 2, 3 and 4. Okay, so this is T. Very sorry for that. I hope it is visible now. Thanks for pointing that out. Yeah, so basically what I was saying is that this H given T is just a representation of list in Prolog, where H corresponds to the first element of the list and T corresponds, or tail corresponds to the rest of the list. Okay, so I hope that gives some clarity on how this definition is framed. So here we are given that sure, better. Yeah, so essentially what I was saying is that let's say you have a list, okay, that has some x number 10, some 10 elements. Okay, I'm not writing down what they are. Let's say they are just x1, x2 up to x10. Okay, so when you write this, you could write this list as this x1, x2 up to x10, right? Or you could also, when you are writing it in a certain formulation, when you're trying to implement or write some program in Prolog as a shorthand, you can also write it as h given t, okay, where the variable h would correspond to the first element of that list and t would correspond to the remaining part of that list, as in this part x2 to x10. Okay, so the reason why this is something that is used in Prolog very frequently is that this is very convenient when we want to access a certain element that is at the top of the list. Okay, suppose you want to write a program that requires you to pick a certain element from the top of the list, do some operation on it or compare it with something and then proceed further on, right? So it's easier to just put the list in this framework of h given head given tails and then pick the list one at a time. Okay, pick the head element of one at a time. So I hope that that clarifies the notation somewhat. And if we go back to the definition of predicate P that is given over here, here we have said that P of this list, where so this is a particular list with H as the head element and T corresponding to the rest of the list. This has length n. This list has length n if P of predicate of T, the tails part of that list, is some other number m and n is m plus 1. So essentially what this is telling you is that, again let me use the same list example. You have 1 2 3 4. Okay, so when you check this first definition or the first predicate P, you say that P of 1 given 2 3 4, this has this list 1 given 2 3 4, or this 1 2 3 4 list, this has length n if just 2 3 4. Yeah sorry again. That's, I should be more careful about this. Sure. So like I said, we start with this particular list 1 2 3 4. Okay, and as per the definition of predicate P, we are saying that P of this list, which is represented in the head tails format, which is 1 is the head, 2 3 4 is the tail. This list 1 2 3 4 has length n if the tail part of that list, which is just 2 3 4, this has length m and n is equal to m plus 1. Okay, so here you are recursively defining the length of the tail part. Okay, so again we can apply the same definition on 2 3 4. Okay, and then we'll put 2 as the head. So then it will be P of 3 comma 4 is length, let's say x, where m is, or I should not write equal to because that might confuse you with the other option that is given. N is m plus 1. M is x plus 1. Again further recursing down, we have, so here 3 will become the head now and 4 will become the tail, right? So we will have, let's say the length of this particular list containing just 4 is y, where x is y plus 1. And if we further recurse down, we will have 4 will become the head, and now the tail part does not contain anything, right? So the tail part will be empty now. And this also takes us back to the base condition, right, where we said that the empty list has a length 0, right? So we know that y becomes 0 plus 1, which is 1. Okay, x becomes 0 plus 1 plus 1, which is 2. Okay, m becomes 0 plus 1 plus 1 plus 1, which is 3, and n finally becomes 0 plus 1 plus 1 plus 1, 4 ones essentially. So we find that the length of this list is 1 2 3 4. Okay, so this definition of predicate P actually gives us the length of the list that is given to us. Okay, so this was just one detailed working I went into. Again, if you put it in Prolog and use the trace command, you'll be able to see all these behind the scenes actions going on. Okay, so I highly encourage you to try that out yourself as well. Alright, so okay, yeah, so here's what we will expect. Okay, so when you run these different predicates P, Q, R and S, P will return n is equals to 4. whereas Q will return not 4 plus but 0 plus 1 plus 1 plus 1 plus 1. And the reason is that you have used an equality over here instead of an is. Okay, so this is something that comes from the technicality of programming. So some of you who might be familiar with programming might be able to understand why that is the case. So when you use the equality sign, you assign a variable something, right? Whereas when you use this is thing in Prolog, this is particular thing, you are actually calculating the sum and then adding it up, right? So finally you have the value 4 over here, whereas in this Q predicate we have the output in this particular notation, 0 plus 1 plus 1 plus 1 plus 1, which we know is equal to 4, but that is not the expected output according to our question, or according to our expectations that we wanted to get a number. We wanted an integer that tells us the length of the list. The third option is of course incorrect, because this, instead of adding the number of elements in the list, it adds the element itself, right? So we have 10 plus 20 plus 30 plus 40, which gives us 100, right? So this is definitely not the length of the list. And again, representing this in this equality terms will give you 0 plus 40 plus 30 plus 20 plus 10, which we know that also sums to 100, but this output is in a different format. So the bottom line is that the question 5, the correct option would be P over here, right? Because we saw P tells us the length of a given list L as the number n. Okay, so I went on for quite a while. I hope it is clear. Any doubts? Okay, that's great then. If so, then question 6 will be easier to answer. So question 6 asks us, we are given the same 4 predicates P, Q, R and S, but here instead of choosing the predicate that tells us the length of a list L, we have to choose a predicate that gives us the sum of the elements of the list L. So as per the interpretations of the definitions that we just saw, which of these options do you think would be correct? C, exactly. Yeah, so that's right. C will give us the sum of the elements of the list, right? So the correct answer would be C, which is the R predicate. Okay then. So if this is clear, we can then move on to the next couple of questions, for which we will be utilizing a common framework. Okay, so let me just go over that framework once. Okay, so here we are tasked with writing a particular Prolog program. Okay, and we are given some some specific predicates. For example, this same as a comma b, this essentially tells us whether lists A and B are same or equal, right? For example, same as 1 2 CD5 and 1 2 CD5 should return a true. Again, you should check this in Prolog as well. Okay, similarly, prefix of A comma B should tell us whether the list A is a prefix of list B. As an example, prefix means that it should come at the front of the list B. Okay, so here you see that this 1 comma 2, this sub list is coming at the front of this bigger list 1 2 CD5. So we can say that 1 2 is a prefix of 1 2 CD5. Okay, similarly, suffix of A comma B tells us that this list A is a suffix of list B, which essentially means that it comes at the end of the list B. So D comma 5 comes at the end of this bigger list, so we can say that D comma 5 is a suffix of this bigger list B. Now another predicate is sublist A comma B, okay, which says that list A is contained in list B in a contiguous block. this essentially means that you have this smaller list 2 comma c somewhere in the bigger list, but this 2 comma c, this appears together. It's not like 2 is at one place and c is at a very far off place. This 2 and c have to appear together. That's why contiguous, right? So this is what a sublist is. Okay, and the last predicate is subsequence. Over here you can have the elements of the smaller list far off. For example, we have 2 comma d as a subsequence of the bigger list, right? And here you see that 2 and d have a c in between them, but we still say that 2 comma d is a subsequence of the bigger list. Okay, so are the definitions of the predicates clear? So Srinivas, no, you have to you have to check the lists exactly the way that they are given. If you compare 1 to CD5 and 1 to DC5, they shouldn't be the same. Again, I'd encourage you to check it on Prolog as well. There's a slight chance that I might be incorrect, so just for the safe side, you should check it out as well. Okay, so if the definitions of these predicates are clear, the task that we are left to do is to fill in the blanks that would actually help us define or implement these particular predicates, okay, in Prolog. So let's tackle each of them one by one. So the first one asks us, let me actually go to the question. So question 7 is based on this particular setting that we just saw, okay? And question 7 asks us the body of same as rule in line 2 will be which of these? Essentially, what will this first blank be filled with? That is what you are asked based on this particular setting. Okay, so maybe you can click a screenshot or a photo of this particular problem setting, because we'll be going back and forth a lot, so you can have a ready reference for you. Okay, so I just give a 1 2 3 countdown, and that's done, and then we can have a look at the options. Okay, so which of these 5 options do you think should go into the first blank? So remember, we want to compare 2 lists and say whether they are exactly the same as each other. Okay, and again we are using the head and tail notation over here. We have the base case that tells us that the empty list is the same as another empty list, and the recursive definition, the second statement, we have a list where A is the first element, A is the head, and AS is the tail, and another list where A is also the head element and BS is the tail. What do you need to when can you say that this A given AS and A given BS, they will both be exactly same as each other? You already know that the head element is the same, so what else do you need to compare? So not necessarily the suffix, right? So you want them to be exactly same as each other. So even if the suffixes are same, there can be some middle part in the list that can be different, right? So you should go with something more robust that tells you that given 2 lists, they are exactly the same as each other. You can use the same as definition itself, right? So essentially this would read same as A given AS and A given BS if same as AS and BS, right? So if you know that the tail parts are same by recursive definition, and you add the same head element to both these lists, then they will also be the same, right? So the first blank should be filled with nothing but same as AS BS itself. Is that clear? Sure, sure. Let me write it down. Okay, so the base condition where the one that you are checking is that, so I'm not writing the whole thing. Okay, so this SA represents same as, yeah. Very sorry again. uh, okay, so this is the base condition. Okay, this is clear, right? Now the second thing that you need to put in is that okay, so this total is one list. Okay, this could be something like this A comma S. This could be, going back to our example, this could be 1 given 2 3 4. Okay, and then the other list could be A given BS. Okay, so here also A is the head element, right? So you know that for this second list also you have 1 over here, and then you have some BS over here. Okay, or some tail over here that is represented by BS. Now you have to define this if condition. So this thing, this whole thing will be true if what is true. Okay, this will be true if this is also 2 3 4, right? So that is exactly what we are writing recursively. So in order to define the same as predicate, we will recursively check whether the tail is also same as each other. Okay, and when you keep reducing your list by removing one head element at a time, eventually you will reach this base condition, right? And this you know is true. So when you trace back the recursive nest, you will arrive at an answer as to whether the two lists are exactly same or not. Does that help somewhat? Sure. Exactly. Yeah. That's perfect. Perfectly summed up. Okay, so couple of doubts in the chat. Um, no, prefix plus suffix is not necessarily the entire list, right? So prefix can correspond to just the first element, the first two elements, first three elements, first four elements, or even the whole list. The whole list is a prefix of itself as well, right? Uh, um, Similarly, suffix can correspond to the last element, the last two elements, last three elements, right? So you can also have the first two elements of a list as prefix, the last three elements of a list as suffix. Okay, and if your list happens to have total of 5 elements only, then yes, prefix plus suffix equals to entire list. But if you have 10 elements in the list and your prefix is only the first two elements, your suffix is only the last three elements, then your prefix plus suffix will not be equal to entire list. Is that helpful, Smara? Okay. That's great then. So if that is clear, then let's tackle the second blank, which is in the definition of prefix. Okay, so now we have to check whether this list A is a prefix of the list B, and the base condition that is given to us for that is the empty list is a prefix of every list, which makes sense, right? So now you are given that prefix of A given AS and A given BS. This will be true if what do we fill in the blank over here? Again, you have to do something with the tail part, AS and BS. Yeah, suffix and prefix can be independent of each other.
So if we have, for example, 6 elements,
Mm-hmm.
then can I say that I have one as first element as my suffix, the last 3 elements as my first element as my prefix,
Mm-hmm.
and last 3 elements as my suffix.
Yeah, you can check that. So the way you are writing these predicates is right. You want to check whether something is a prefix of something or not. Let's take your example. Let's say that you want to check whether 1 is a prefix of this list that contains 1 2 3 4 up to 6. Okay, so technically the way you implement your program, this should return a true, right?
Yes.
But if you give something like 2 comma 3 over here, so 2 comma 3 is not a prefix of 1 2 3 4 5 6, then it should return a false. Similarly, if you want to check suffix, then you can say that 6 is the suffix of this whole list containing numbers from 1 2 3 4 up to 6. Or you can even say that 5 comma 6 is a suffix of this bigger list containing numbers for 1 2 3 4 up to 6. But you cannot say that 4 comma 5 is a suffix of this big list containing numbers from 1 2 3 4 5 6. Okay. Okay, so coming back to the definition of this prefix of predicate, what do you think will be the blank over here? Again, think in a similar way as we did for the previous question. We already know that the head element is the same, so we can safely say that okay, so the head element of the smaller of the two lists are same. So as of now, the prefix condition is strong. It's going strong. What do you need to check next? Not same as, right? Because you want to check whether it is this whole A given AS list is a prefix of A given BS or not. Yeah. So what will you fill in? Again, this will be recursive. It will be prefix of itself, right? Prefix of AS comma BS, right? So when the head elements are the same, the only thing that you need to check is whether AS is a prefix of BS or not. If AS is a prefix of BS, then adding the same element to the head will also remain the prefix condition to be true. Let the prefix condition to be true. Okay. I hope that is clear. Okay, thanks for that. So then we can move on to the next question, which asks us about the suffix of rule. Okay, So again you are given these different options, suffix of same as, suffix of, prefix of, sublist and subsequence, and you have to choose which of these would fill in the third blank. And remember, the third blank now is the base condition that you are checking. So what do you think will be the correct answer to fill this blank? Suffix of as bs, or essentially as is a suffix of bs if, what do you think? So I'll give you a hint. Here you need to check whether something is exactly same as each other or not. See, here you are given the second statement, but not the base condition. Okay, so what do you think could the base condition be in case of when we are trying to look at the suffix? What we are going to do is we are going to remove one element from the top one by one until we are left with some last portion of the bigger list that is dash as the smaller list. It would be same as, right? See, what you're doing is you are given a big list. Okay, you want to check whether, let's say, 6 is a suffix of 1 2 3 4 5 and 6. Okay, so in the second statement what you are told is that one at a time you are going to remove the head of the list. Okay, that's essentially what you are doing over here, right? In the sixth line we are given that suffix of as comma b given bs, right? So as is a suffix of b given bs if as is a suffix of bs. So notice that how we cleverly got rid of the head element, which is b, right? So we will remove one element from the top of the list one by one until we are left with some last portion of the bigger list that is same as the smaller list that we want to compare our bigger the suffix with. So we removed 1, we removed 2, we removed 3, we removed 4, we removed 5, and essentially we will be left with 6 and 6. So now we need to have a base condition which says that if we are left with two lists that are exactly same as each other, then we have reached the base condition. So here the dash should be filled with same as as comma bs.
Can you explain it once more, sir?
Sure. Okay, so okay, let me take a two list suffix, two element suffix. Okay, so let's say 5 comma 6 is what you want to check whether this is a suffix of 1, 2, 3, 4, 5, 6. Okay, so this is what you want to check. Now the second statement that is given in the definition, let me go back to that. That tells us as comma b given bs. Okay, so if you write your list in this form, so this 5 comma 6, this is a suffix of 1 given 2, 3, 4, 5, 6 if 5 comma 6 is a suffix of 2, 3, 4, 5, 6. Does this make sense up until this point?
Yes.
Okay, that's good then. So similarly, we are going to step by step, we are going to get rid of one of these elements from the top of the list one by one. Okay, so just like we removed this 1, right, in the next step we'll remove 2, then we remove 3, then we remove 4, and now we are left with just 5 comma 6 from the bigger list and just 5 comma 6 in the smaller list that we want to check whether is a suffix or not. So now what operation do we need to perform? We need to check whether these two are exactly same as each other or not, right? So that's why we are using the same as condition in the base condition. Okay, so that answers suffix of, yeah. Mm-hmm.
How the sentences sound?
Repeat how, what is?
How do you spell them?
How do I spell the lists?
Can you just read what you've written in your language?
Okay. So I have skipped out a lot of notations, so excuse me for that. Essentially what we have written over here is we want to check whether 5 comma 6 is a suffix of this bigger list. 5 comma 6 is a suffix of 1, 2, 3, 4, 5, 6 or not. Okay, for that we know that the second statement that is given to us in the definition of suffix of is that this 5 comma 6 is a suffix of this format, this representation of this bigger list 1 given 2, 3, 4, 5, 6 if 5 comma 6 is also a suffix of 2, 3, 4, 5, 6. Okay, so this is how you will read it out, and then you will recursively check whether 5 comma 6 is a suffix of 2, 3, 4, 5, 6. For that again you will frame this 2, 3, 4, 5, 6 as 2 given 3, 4, 5, 6, and in that step 2 will get removed. Then you will check whether 5 comma 6 is a suffix of 3, 4, 5, 6. Okay, in the next step 3 will be removed. Then you will check whether 5 comma 6 is a suffix of 4, 5, 6. Then 4 will be removed. Then you have to check whether 5 comma 6 is a suffix of 5 comma 6. How do you check that? By seeing whether they are exactly same as each other. Okay, okay, okay. So the only two blanks that are left are sublist and subsequence. So I'll give you 5 minutes to think about these two, and yeah, then you can share your answers in the chat box. Okay, so there's a question in the chat box, so I'll just address that. So the question asks whether we will apply the same logic of using same as when we were defining our prefix of function. And the reason why we are not going to use same as over there is this. Okay, so like I showed this example, let me show one more example. So in prefix of, what you are doing is you are checking whether 1 comma 2 is a prefix of 1 2 3 4. Okay, and the second condition that is given to you is so the base condition that is given to you is prefix of empty list bs, which means that empty list is the prefix of everything. That's well and good. Now when you frame this prefix of a given as and a given bs, what will you get over here? You will have prefix of 1 given 2 is this a prefix of 1 given 2 3 4. Okay, so in order to check, so this will be true if what is true, right? So we know that the first element 1 is same in both the lists. Now we need to check whether the tails part is not same, whether the tails part is a prefix or not, right? So 1 given 2, this will be a prefix of 1 given 2 3 4 if two is also a prefix of 2 3 4, not same as 2 3 4. Okay, I hope that resolves the confusion. I know these are a bit very convoluted things to grasp in the first go. I completely agree with that, and I myself, when I was taking this course, I spent a decent number of hours just scratching my head about these things. But the way to, I would say, the way I took to understand them is again to use Prolog. Okay, so the more you experiment with Prolog and the more you use a trace function to see what is happening exactly, how it is comparing the two things, the two lists, list or sublists or whatever that is, you'll get to start to get a better understanding of how we are implementing these things in Prolog. Okay, so
here my A's is 1. In the first case, A's is 1, B's is 2, and then with the comma. And in the second list, my A's is 1, B's is 2 3 4.
okay, sorry, can you come again please? I also got a bit confused. Or let me say what I understand, and then you tell me whether your understanding is the same or not. Will that be okay?
Yeah.
Okay, so here we have 1 as A, 2 as As, and here we have 1 as A and 2 3 4 as Bs. Is that what you were also thinking? Okay, that's great.
So if A is same, what can we do is we can just recursively move the second list, because elements one by one, and then we can check at the end that if the A's is equal same as B's, then the condition is satisfied.
No, no. See, you are thinking of the recursion in the opposite direction, right? So the way the colon and dash is defined in Prolog is x if y, right? So not x, uh, uh, not x hence y, x if y, right? So you need to think of the recursion in the correct direction. So essentially what you are doing here is, if 2 is a prefix of 2 3 4, then 1 comma 2 is a prefix of 1 2 3 4. Okay, so you start from the base condition and then you build up to the top. Okay, so you start from, okay, empty list is a prefix of some list. Okay, then you say whether you add something to it, let's say 2, and then you check that that is a prefix of the bigger list or not, and then you add something else 1 to it, and then you see 1 2 is a prefix of 1 2 3 4 or not. Okay, so intuitively, to understand, it's okay to say that, okay, I'm removing one element at a time and then I'm checking whether these two are same or prefix or suffix or not. Okay, intuitively for our understanding that's okay, but the way Prolog implements it is from bottom to top. Is that helpful, or did I confuse you even more? I'm sorry about that, but yeah, I would suggest that you implement this in this Prolog, based on the definition that we have over here, right? So we are filling these blanks one by one, right? So you write this code in Prolog exactly the way that we are writing the answers, and then you check different cases of whether something is a prefix of something or not, and then you use the trace condition to see how that is being checked in Prolog. Okay, unfortunately I don't have Prolog installed on this system that I'm using right now, otherwise we could have done it today itself, but maybe next week I'll try to get it installed on my system. Okay, okay, so let's tackle the last two blanks as well. So the second last blank is sublist. Okay, so we have to give the base condition for sublist, and we are given the second thing is that A given AS is a sublist of B given BS if A given AS is a sublist of BS. Okay, so how do you interpret it? Remember, in sublist you need to find contiguous blocks of some contiguous middle block in the list. Okay, so what do you do is you keep removing one element from the front of the bigger list. Again, I'm telling in an intuitive way. So Arun, I think you are close, but think in the opposite way, right? We need to check a sublist and we are removing one element at a time from the front. So do we need to check the suffix or the prefix? Yeah, it will be prefix of, right? So again, take the same list an example. So you have the big list as 1 2 3 4. Okay, you want to check whether 2 comma 3 is a sublist of 1 2 3 4 or not. Okay, so 2 comma 3 will be a sublist of 1 2 3 4, 1 given 2 3 4 if 2 comma 3 is also a sublist of 2 3 4. Make sense? Right? Yes, no, not at all, anything? Okay, so let us write it down. See, we need to check sublist of. Okay, so again I'm using SO again, so here it corresponds to sublist of, not suffix of. Okay, so don't confuse that again. Yeah, I should share the screen. Okay, so we want to check whether 2 comma 3 is a sublist of 1 2 3 4. Sorry about that. Right, so we can say that 2 comma 3 will be a sublist of 1 2 3 4. Essentially what I mean is that whether 2 comma 3 is contained somewhere together in the middle of the bigger list. Okay, that is what I want to check. So 2 comma 3 is a sublist of 1 2 3 4 if 2 comma 3 is also a sublist of 2 3 4. Right? So now what you need to check is whether 2 3 is a prefix of 2 3 4 or not. If you already have a prefix, you have reached some middle portion of the bigger list that has that contiguous block that you want to consider as a sublist. Okay.
If it is a 1 2 3 4,
Mm-hmm.
sorry, 2 comma 3 comma 2 3 4. So 2 comma 3 is a prefix of 4, sir. We are leaving that 1 here, right?
Yeah. So because we had represented it in this heads given tails format, right? So you were checking whether 2 comma 3 is a sublist of 1 given 2 3 4. So 1 given 2 3 4 is the same as 1 2 3 4. It's just that we are representing this in that particular form where 1 is the head and 2 3 4 is the tails. Okay.
Can you repeat that, sir? The second line, if 2 comma 3 is a sublist of 2 3 4.
Yes. So essentially what we are doing is, if 2 comma 3 is a sublist of this 2 3 4, then we can say that 2 comma 3 is also a sublist of 1 2 3 4 or 0 1 2 3 4 or minus 1 0 1 2 3 4. Anything you keep adding at the front doesn't matter, right?
So how we are concluding about that prefix suffix here?
Yeah, so you were given this condition in your definition, right? The second statement. Now you need to choose your base condition appropriately so that whenever something like this is reached, you can stop and conclude that yes, I've reached the base condition. We can terminate and give a result, right? So here, instead of using something like a same as, if we can say that 2 comma 3 is a prefix of 2 3 4, we can say that 2 comma 3 will be a sublist of 1 2 3 4.
Yes.
Right?
Yes, okay, now I understood.
Okay, that's great. Mhm.
Is present at the end, so we would consider 3. For example, I have a list 1 2 3,
Okay.
0 1 2 3. Okay,
Okay.
and for that, if 2 3 is a sublist, if 2 3 is present in 0 1 2 3, so then can I say that if 2 3 is a suffix of 0 1 2 3, sorry, if 2 3 is a suffix of 1 2 3, then it would be also the sublist of 0 1 2 3.
For this specific case, yes, but when you are checking for a general case of whether something is a sublist or not, then you can't always go with suffix, right? Because if you consider only the suffix, then you might not be able to check whether something is present in the middle of the list or not, because suffix only looks at the last portion of the list. So the specific example that you gave, yes, it is framed in a way where the suffix happens to be the last two portions, the last two elements of the list, 2 3 happen to be the one that you are considering as the sublist. But in general, it's better to use this prefix instead of suffix.
Thank you.
Yeah. Okay, so we are nearing the end, so let me just quickly mention what subsequence blank will be, and then I'll ask you to ponder over it, and maybe we can discuss it further in the next live session if it's not clear within the limited time frame today. Okay, so the subsequence is defined in a way where the base condition tells us that subsequence, so empty list is a subsequence of everything. Again, makes sense. Okay, and the last fact that is given to us is that if uh, a given as is a subsequence of bs, then a given as will also be a subsequence of b given bs. So what will be some intermediary blank that we are going to have over here, or not an intermediary, but you can say another way of checking whether something is a subsequence or not. So a given as can be a subsequence of a given bs if a given as is a subsequence of bs. This is one condition.
Can we go back to the screen? The question is
Ah, okay. I'm so sorry about this mishap today. Uh, yeah, yeah. So basically, the subsequence definition was that empty list is a subsequence of everything. Okay, and then whether a given as is a subsequence of a given bs, that can be checked based on two different approaches. One is if a given as is a subsequence of bs itself, or another way could be if as is a subsequence of bs itself, right? So remember, here in subsequence we don't want contiguous, right? Those elements can be far apart from each other. Okay, so I understand that this is not everyone is not convinced with the answer, so I'll let you chew on it for a while, think about it. Okay, and then we can discuss it again in the next live session if not clear. Okay, I'll repeat. So the answer is that the blank will be filled with subsequence as comma bs. Okay, so now your task is not just your, Aryaman, everyone's task is to think about why that will be the right answer. Okay, and then we can discuss it further in the next live session. The reason why I'm hurrying is that there are two more questions that I wanted to cover, which I will quickly mention. Okay, so consider the built-in predicate append. Okay, so Prolog has some built-in predicates. Okay, so this essentially tells us that x appended with y gives us z. Okay, so when you list a query where x and y are variables, and you know that your appended list should be something like 20220228, what is the total number of solutions listed by Prolog? So here your answer would be different possible values that x and y could take to render this total list that is given to you as the answer. An example could be x could be an empty list and y could be the whole list 20220228, or x could be just 2, y could be 02202228, or x could be 20 and y could be 220228. Okay, so if I represent this in Prolog, you will get something like this, right? So the first possible case is where x is empty, y is the whole list. Then another possible situation is where x is 2, y is 02202228. Another possible condition is x is 20 and y is 220228. So if you keep on doing that, you keep on taking one element from y and adding it to the end of x, right? And then you will have these different possible configurations that x and y could have to render the final list. Okay, and this is what Prolog will return to you. So again, this is again something that I would encourage you to do yourself and check it out and understand why that is happening. Okay, and so the answer for this will be 9. You can verify that. And the last question is, we have to select the correct options from all of these. This is a recall based question, and all FOL formulas can be expressed as Horn clauses. This is wrong. Okay, SLD resolution always terminates with the solution proof. Again wrong. And because this is wrong, the third option is also incorrect. SLD resolution always terminates is also wrong. So the correct option here is none of the above. Okay, that concludes the questions for today. So again, I would like to conclude by saying I highly encourage all of you to actually run all these Prolog programs that we discussed today, either in online Prolog or the Prolog installed on your system. Okay, do it yourself, and I'm sure that will help you improve your understanding if it's not already better.
Sir, a final thing,
Mhm.
unifiers. In case of unifiers, can you explain? That is one simple logic is there. Constants cannot be replaced with a constant, but variables can be replaced with a constant. That is only the hint, right, sir?
This is one of the hints. So constant can be replaced with another constant when they are exactly the same. Like if you have
Exactly same. That is only.
yeah, so if you have a constant sun and you have another constant sun, as in sun, then you can replace those two with each other. But if you have one constant sun and another constant moon, then you cannot replace those two with each other. But if you have a variable x, let's say x, the name itself says that x is a variable, in the sense that it can take different possible values, right? Its values vary, that's why it's a variable,
Okay.
right? So it can take sun, moon, anything.
Okay. Thank you so much, sir.
Okay. uh,
So I had a doubt and question about that.
Question 4 from today.
Yes, sir.
Okay, let me go back. Yeah, yeah, go ahead.
Yes, sir. Sir, here it is given if successor of x is less than y, then x should be less than y
Mm-hmm.
in less than 1
Yeah,
definition.
yeah.
Sir, so isn't it always correct? So the successor of x should always, if it is less than y, then successor of x minus 1 should definitely be less than y.
Yeah, but you check the two condition that we checked, right? So if you replace sx with 2, successor of x with 2 and y with 1, then x will become 1, right? If successor of x is 2, then x is 1. That's okay, right? uh,
Yes, sir.
yeah, so if 2 is less than 1, then by this definition 1 is less than 1. That doesn't make sense, right? So for it's for that reason that we are saying that this definition is not exactly correct. Okay. Shashi, yeah, I'll try to upload it today, but it seems difficult because I have a couple of things lined up after this one after the other, and I don't think it'll be possible for me to get time, but I'll try. Okay. If not, tomorrow morning. uh, Thanks for understanding. Okay, I don't have the answer to your second question, so I'm going to avoid that. Uh, this was for a question Sashi put in the chat box. Okay, so let's dismiss today and meet next week. Okay, see you all. Bye bye. Have a good rest of the evening.